Hello students, welcome back. So in this session, I'm going to show you the need for different types of data types. Now, if you remember, NumPy offers you many different types of data types. So why do we even need all these data types? So I'm going to run this experiment and a little test just to show you and convince you the importance of all these data types. Now, NumPy has integer data types. Okay, in integer data types, again, there are two kinds. There's an unsigned and there is a signed. In your unsigned, you have this depending on the bits, you can have NP uint 8, you can have uint 16, 32, and 64. So let's look at this one. What is this telling me? This is telling me that this one is an unsigned 16-bit integer, all right? And this can hold the numbers between 0 to 65,535. So if you know your numbers are going to be between this range, it's always going to be in this range, then you want to use this data type. All right, then let's look at the assigned integer data types and their ranges. So let's look at this one right here. This one is telling me that this is int 16 holds takes it occupies 16 bits of your memory, and the minimum value is going to be between minus 32 768 and the maximum value is going to be 32,767. So as you can see, in your signed integer types, again you have four kinds. In your unsigned, you have four types. Then you have float data type. In float, you have float 16, you have float 32, you have float 64, you have float 128, depending on how much precision you want. In other words, how many numbers you want after decimal digits, you want to use one over the other. If you want a high precision, you want to go with maximum, which is float 128, if your computer supports it. Otherwise, go with float 64 or float 32 or float 16, depending on your level of precision. Now, why do we even have so many data types in NumPy? Well, number one, memory efficiency. So different data type require different amount of memory. So for example, your int 8 uses 1 byte and 64 uses 8 bytes. If you know that your numbers are always going to be between, let's say, 0 to 100, you want to use a smaller one, right? And so this actually helps you with your memory efficiency. Performance. Now when you do like numerical computation on a smaller data types, they tend to be a lot faster. So this is one of the advantages. So if you know your data type right from the get-go, right from the beginning, this is going to make your numerical computation a lot faster. Precision. So precision, basically what it does is, for example, float 32. Okay, float 32 will have a less precision than float 64. So if you want a high precision, meaning more numbers after the decimal, and you want to make sure that all those numbers are accurate, then you want to use float 64. So let me show you by running an experiment, like how memory efficiency, performance, and precision, okay, how they actually help you by choosing a right data type. So first you want to do is import your NumPy as NP. All right, import my NumPy as NP, run this. And then let's deal with the memory usage. Let's try to understand the memory usage. So let's say you're working with one-dimensional data and the numbers are always going to be between 0 and 200. You already know from the beginning your number is going to be between 0 to 200. And let's say the size of your data is 10,000. Okay, there are 10,000 elements inside this. Well, let's create four different kinds. Let's create an int 64. Okay, I'm creating four different data types. So let's look at this one right here. What this is doing is creating a random numbers between 0 and 200. Okay, by the way, the reason is 201 is because if you remember, this function actually is going to create the numbers between 0 to 200. So you want to put 201 over there, one number higher than that. Okay, so I created numbers between 0 to 200, and how many I create? I create n, which is my 10,000. So I create 10,000 and I create an array of 10,000 elements in it that will have numbers between 0 to 200. And the type would be int 64. Likewise, this right here, this one creates a NumPy array of 10,000 elements, and the number is going to be between 0 to 200. And the data type would be int 16. All right, now if you want, you can actually take a look at some of them. So let me just come over here and comment this line out. So I'm just printing the first 259 values for this one right here. Okay, I'm just printing the first 259 values. And as you can see, this is my first 200 values. And these are my values. You see, every number is between 0 to 200. All right, so I just printed the first 259 values. Now, let's check the memory usage. Let's run this and let's check the memory usage. Look at that, int 64. It's occupying 80,000 bytes. Unsigned integer, okay, unsigned integer 8 is occupying 10,000 bytes. So The conclusion is this: if you know if you know that your data is always going to be between 0 to 200. Okay, if you know your data is always going to be 0 to 200, then use np uint 8. Okay, because that number, if you remember, if you go on top, right there, you see np uint. This with the range is from 0 to 255. So if you know your numbers are going to be between 0 to 200, choose this one right here. Okay, now let's look at performance. Let's see how performance does. Come down, paste it up, not this one, other one, come down. All right. So let's perform some numerical computation. I'm going to do numerical computation with NP int16 and int64, just to show you, just to compare like how much time it takes. So I create two arrays with int64 data type, okay, and then I also create two arrays with int16 data types. And what I'm going to do, I'm going to do some mathematical computation between these two arrays, okay, and I'm also going to do the same thing over here. Okay, now, first I do is check my memory usage. Okay, I'm showing you the memory usage. So let me run this first. So this is going to print out my memory usage. So if you go down, well, there you go. Memory usage, it tells you is 800 megabyte and this is 200 megabyte. So int64 is occupying 800 megabyte. All right, now let's start this program. Start equal to time dot start, time dot time. So basically this is gonna tell you what time it started. Then I perform some heavy computation over here. This is my heavy computation function. It doesn't really matter what that is. Just it just can be any crazy function. Okay, it's gonna do some type of some crazy math to it. It's gonna multiply x by y to the power 2. Then at the end it's gonna do all this thing. Then at the end it's gonna add the numbers. Okay, so I do my heavy computation. Now this time I'm doing heavy computation with int64. I'm taking two int64 numbers and I'm doing heavy computation with that. Then I'm calculating my end time, like what time it ended. And then I'm printing my time. Okay, I'm printing the difference between my end time and start time. So that's going to tell me how much time it took. Same thing now I'm doing again. This time I'm using int16 over here. Okay, this is my two numbers with int16, and I'll do the same heavy computation, and then I print my computation time. And as you can see, the computation time for int64, look at that, is 5.34 seconds. 5.34 seconds. And look at with int64, it's 1.69 approximately seconds, 1.69 seconds. Right? How fast was it, by the way? Let's compare that. How fast? Well, you can actually just say you can just type 5.3 approximately divided by 1.69, 1.69, and run this cell, and that's going to tell you how fast. It was almost three times faster. You see, 3.13, almost three times faster. So, what is the conclusion? Choosing the right data type speeds up your computation. Okay, so you want to make sure you choose the data type that is appropriate for your data. So you don't want to choose and higher ones. If you know your data is going to fit into int16, then choose the int16, because as you can see, it takes less time to do computation. Okay, precision. Now let's talk about precision. So come over here, let's create few cells. So let's compare compound interest. We know from a high school like how compound interest was calculated. I'm assuming you know. So we're gonna calculate compound interest using float 32 and also using float 64, and we're gonna compare them. Okay, we're gonna compare the result. So let's say this is my principal amount, my rate, okay, 5% annual interest, and my year. I'm actually, let's say, simulating for 1,000 years. So what I'm doing, I'm taking my amount 60. I'm taking my principal amount, right? Taking my principal amount, converting into float 16. All right. Then initializing my amount 16. Then I'm calculating my basically compound interest for the 1,000 years. So I'm using this for loop right here. Okay, that's going to calculate my amount 16, which is after 1,000 years. What is going to be? This is going to be using float 16 simulation. Then I'm using float 64 simulation. I'm taking my same principal. Okay, I'm taking this principal amount and I'm converting into float 64. This is how you convert into float 64. And then I'm doing exactly same thing what I did over here. I'm calculating my total amount after 1000 years. So I'm running through a for loop, and that calculates the total amount after 1000 years. Then I'm also calculating my exact value. This is the formula that we all studied in our high school, that how do you calculate the exact amount? And if you remember, it's principal times 1 plus rate to the power 100 years. Okay. And then after I run this, okay, then I print my amount 16, which is my amount that I calculated using 16-bit. This is a different amount, which is calculated using 64-bit. And this is my exact amount. And look at that. Look at this value. This is my 16-bit, 64-bit, and exact result. And just by looking at this, you can tell that Uh, look at that. Let's compare exact. Let's look at this exact value right here. You see, exact with float 64, they tend to be same, but they kind of like start drifting over here. Like somewhere over here, they start changing, right? You can see up to here, the numbers are same. Between float 64, between this and this, the numbers are here. Up to here, they're same, right? Up to here and here, they're same. Now let's look at float 16. Well, the numbers are same up to here, up to here. Okay, this is 15463, and this is 15463, and after this becomes 189, and this becomes 200. So as you can see, float 16, it starts drifting away from its true value after only like 1 2 3 4, after 5 digits. And then I'm calculating the difference between your exact amount and the amount 16, and also exact amount and amount 64. And you can see the error for your float 16 is a lot higher. Okay, the difference between this amount, and this amount is a lot higher for your float 16, and the difference between your float 64 result and your exact result is very less. You see, the error is small. So I hope this convinces you the need for data types.